Hi, I'm Mark Barsamian. In this video, I'll be doing applications problems involving basic differentiation properties. The reading for this video is from section 2.5, Basic Differentiation Properties. But section 2.5 doesn't actually have any examples similar to what I will do in this video. The closest example is from section 2.4, example 8 on the bottom of page 139. The relevant homework problems are these three problems from section 2.5. Before starting the examples for this video, I want to talk a bit about what I've been referring to as the most important concept for the first month of the course. This concept, when one can cancel and why. This has come up, for instance, in expressions like this. If I substitute h equals 0 into that difference quotient, we get the quantity 0 over 0, which is not a real number. It does not exist. So we can't cancel 0 over 0. But when you're computing the derivative, using the definition of the derivative, you're doing this. You're finding the limit of that expression. And when we did those kinds of calculations, we would do some arithmetic steps and arrive at some step where the expression is an expression of this form, the limit of h over h times something. And since this is a limit, as h is approaching 0, we know that h is not equal to 0, so we can cancel h over h. That was the key step in being able to compute the derivative. At this point in the course, though, our attention turns to learning derivative rules, which allow us to compute f prime without having to use the difficult limit formula from that definition of the derivative. The issue of when we can and cannot cancel terms will no longer come up. For the next month of the course, a different concept will be the most important concept. Recall what we've learned about the relationship between the derivative of a function, the instantaneous rate of change of a function, and the line that's tangent to the graph of a function. These three quantities are equal. The instantaneous rate of change of the function at x equals a, the slope of the line that's tangent to the graph of f at x equals a, and the value of the derivative of f of x at x equals a. And they're all denoted by this symbol. So that idea that those three quantities are equal is going to be very important, and it's going to be helpful to have a diagram that illustrates the equality of these quantities. Here's a diagram of those three equal quantities. We have the value of the derivative of the function at x equals a. We have the number that's the instantaneous rate of change of the function at x equals a. And we have the number that's the slope of the line tangent to the graph of the function at x equals a. Now in this video, we'll study three examples involving applications. Remember that that means that we'll be using functions to model behavior of actual real-world situations. All three of the examples will involve the rate of change of some quantity. And so the concept of the three equal quantities will be central. And this diagram of the three equal quantities will be helpful for visualizing the structure of the problems. So our first example is similar to 2.5, number 89. A startup company introduces a new product, and total sales are described by this function. In this function, t is the time in months since the product was introduced, and S of t is the total sales in millions of dollars at time t. Question A is to find S prime parentheses t. Let's do that. Remember the format of the solutions. We start by writing the thing that we're going to be computing, and then we set up the calculation that will give us that thing. But we don't actually do the calculation in the first step. We just set it up. And also notice that we have d over dt. I should make that a little clearer, because the variable is time, t, not x. All right, well, we'll use our basic differentiation rules. So when we use the sum and constant multiple rule, notice that we end up with the sum of two terms, and the constant multiples have slipped right through those derivative symbols. Now we get ready for the next step by writing down the things that are not going to change. We're going to have a minus 0.01 times a big pair of empty parentheses and a plus 0.36 times a big pair of empty parentheses. In the left pair of parentheses, we'll put the result of this derivative, which will be computed using the power rule with n equals 3. So remember, up here we started with an expression that could be thought of as the left side of the power rule. It has the d over dt, and it doesn't have any arithmetic going on inside of it. Down here we have what could be thought of as the right side of the power rule. The d over dt is gone. We have brought down the old exponent to the front, and we have computed the new exponent using some arithmetic. For the right term, we're going to compute the derivative that's going to go in these empty parentheses using the power rule with n equals 2. We know that because of that number 2 in the exponent. The previous derivative, we knew that we had n equals 3 because of that number 3 in the exponent. So the result will be, notice in both of these derivatives, I don't do that fairly simple exponent calculation in this step. I save that for the next step. So there's our derivative. Remember, the format of this layout tells us that this thing that we started with is equal to this thing that we ended with. S prime parentheses t equals this expression. Let's go on to the next part. Part B says to find S parentheses 10 and S prime parentheses 10. Remember that that symbol means that we're going to substitute t equals 10 into the formula for S of t. So there's our formula for S of t. We have to substitute t equals 10 into that formula. So our result is that S parentheses 10 is the number 26. Question B, we're supposed to find S prime parentheses 10. Remember what that means. We're supposed to sub t equals 10 into S prime of t. There's our formula for S prime of t, so let's do the substitution. So our result is that S prime parentheses 10 is the number 4.2. Let's go on to the next part. The next part says, write a brief verbal interpretation of your result from B. Now what does this mean? This has actually come up before when we've done applied problems. To write a brief verbal interpretation means, what does this mean in terms of sales? Remember that we have a problem where we're using a function to model sales of a product. So a brief interpretation means to explain what that mathematical result tells us about the sales of the product. Let's go back and look at those results from B. One result from B was this, S parentheses 10 equals 26. Well, what is the function S telling us? Let's go back up and look at that. S of t is the total sales in millions of dollars at time t. So this symbol stands for the total sales in millions of dollars at time t. The value of that is 26. $26 million, and the time is 10 months. So in other words, so that's our interpretation of one of the results from B. Let's go back up and look at the other result from B. The other result from B was this one, S prime parentheses 10 equals 4.2. Now we have to think about what that means. Here is where the diagram comes in. S prime parentheses 10 is one of those things. And this diagram tells us that that is the same as this. So S prime parentheses 10 was the number 4.2. That means that the instantaneous rate of change of our function at time 10 is 4.2. Let's go down and write that up somehow. So there's the description. Notice that the idea of S prime parentheses t became this idea of the rate of change of sales. Also, notice that the abstract mathematical result was just a number. S prime parentheses 10 was the number 4.2. But when we interpret that, we have to add units to our interpretation. So our interpretation talks about time with a unit of months. So t is 10, but that means 10 months. And the result was 4.2 for S prime parentheses 10. That means that sales are increasing at a rate of $4.2 million per month. So the rate of increase has a unit, and the unit is whatever the units are for sales divided by whatever the units are for time. Let's go to question D. Question D says to illustrate our results from B using this graph, this given graph of S of t. So let's go up and look again at our results in part B. In part B, one of our results was this. S parentheses 10 equals 26. Well, that means that on a graph of S of t, when t is 10, the y value is 26. What about our other result from part B? Our other result was this. S prime parentheses 10 is equal to the number 4.2. So again, let's go back up and look at our diagram. S prime parentheses 10 was 4.2. That tells us that the slope of the line tangent to the graph of f at x equals 10 is the number 4.2. So the diagram helps us visualize our question. So to illustrate that on this graph, we have to draw the tangent line at t equals 10 and label it with its slope. That's the end of that example. Let's go on to the next example. Example 2 is similar to 2.5, number 91. In this example, a phone manufacturer had planned to spend $2 million on an ad campaign for a new phone. But they're considering increasing their advertising budget. Their vice president of marketing has a model that predicts the sales of the phone will be described by this function. N of x equals 20 minus 12 over x, where x is the number of millions of dollars that they spend on the ad campaign, and N of x is the total number of millions of phones that will be sold. So question A says, find N prime parentheses x. Well, notice that our function N of x is not written in power function form. It's written in positive exponent form. So let's convert to power function form. So there's the power function form of the function. Now we can take the derivative easily. Here in this step, we use the sum and constant multiple rule. Notice that this constant multiple of 12 slipped right through that derivative symbol. But this constant function of 20 doesn't come through the derivative symbol. It has to stay inside. It's not a constant multiple. It's a constant function. Now we'll use the constant function rule and the power rule. So you can see that When we use the power rule, we started with something which looks like the left side of the power rule. It has the d over dx, and it has the original exponent. We replace that with this new expression, which looks like the right side of the power rule. Notice the d over dx is gone. The old exponent has been brought down in front, and there's a new exponent that's obtained using some arithmetic. Then we simplify. Now let's go on to part B. Part B, we're supposed to find n prime parentheses 2. So remember, this symbol, n prime parentheses 2, does not mean to find the derivative of 2. The derivative of 2 would be the number 0. What that symbol means is this stuff. It means substitute x equals 2 into the formula for n prime parentheses x. Let's go on to question C. Write a brief verbal interpretation of our result from B. Let's go back up and look at that result. The result from B was that n prime parentheses 2 was the number 3. Let's go back up and look at our diagram. We found that n prime parentheses 2 was the number 3, and that corresponds to this. That number is the rate of change of the function. Now, rate of change is a little bit subtle in this example because the variable does not represent time. It represents the number of dollars spent on advertising. So when we write about this, interpreting it in terms of the sales, we have to write about the change of advertising dollars spent, not change in time. So there's our interpretation sort of by the book. Number n prime parentheses 2 equals 3. That just tells us that the instantaneous rate of change is 3. We have to tack on the units, millions of phones per millions of dollars of spending on ads. Whatever the units of n are, that's millions of phones, divided by whatever the units of the variable x are. That's millions of dollars of spending on ads. And so this circled equation involving the derivative symbol translates literally into this sentence about instantaneous rate of change. Now, I don't actually find that helpful. I'd like to put this in maybe better words. What this is telling us is how much we can expect the number of phones sold to increase if we increase the number of dollars we spend on ads. So we get roughly 3 million more phones sold per $1 million of extra spending on ads. So in other words, we roughly sell 3 more phones for every dollar of additional spending on ads. In other words, every additional dollar spent on buying ads will result in roughly 3 more phones sold. Let's go on to question D. Question D says to illustrate our result on this given graph. So let's go back up and look at our diagram again. We have this quantity, n prime parentheses 2 equals 3. In terms of the graph, that's the slope of the line tangent to the graph at x equals 2. So we have to locate the place on the graph where x equals 2. That's this point. Now we could actually get the xy coordinates of that. N parentheses 2 is the number 14, so this is the point 2, 14. And our previous result was that n prime parentheses 2 equals 3. We illustrate that by drawing a tangent line and noting its slope is the number 3. So according to this model, if the company spends $2 million on ads, they'll sell roughly 14 million new phones. But for every additional dollar they spend on advertising, they'll sell roughly 3 more phones. That's the end of that example. Let's go on to the last example for the video. The third example is similar to 2.5 number 97. We have a study that shows the number of words that a student studying a new language can learn is described by this equation. There's a typo here. In this equation, x is the number of hours a student studies, and y is the number of words that the student learns in that time. So question A is, find the rate of learning after 1 hour and also after 3 hours. What does that mean? Well, here's another case where it is helpful to go back up and look at our diagram. We are being asked about the rate of learning. In other words, the instantaneous rate of change of the number of words that the student knows. This diagram points out that that number is equal to this number. So in other words, if you want to find the rate of learning new words, find the derivative of the number of words they know. Part of the objective of this problem is to test whether you understand the connection between these words, the rate of learning, and this symbol. That when you see these words, you make the connection that you find that quantity, that rate of learning after 1 hour, by finding this quantity, y prime parentheses 1. Well, so what should our strategy be? The strategy should be to find y prime parentheses x, and then substitute x equals 1 and x equals 9. So before we can find the derivative, it will be helpful to put the function in power function form. So the function is given in radical form, and we converted it to power function form. So now we can find the derivative. So in the first step, we used the constant multiple rule. That constant multiple 6 slipped right through that derivative symbol. The second step, we'll use the power rule with n equals 1/2. So there's our derivative. Notice that when we finished taking the derivative, we had something that was in power function form, which is not always the clearest form for working with functions. So we converted to radical form. The original function was given to us in radical form. We put it into power function form because that's the form we need it to be in to find the derivative. Now remember the strategy. The strategy was to find y prime and then substitute x equals 1 to get y prime parentheses 1, and substitute x equals 9 to get y prime parentheses 9. There are our values. S prime parentheses 1 equals 3. That's one result. And the other result is that S prime parentheses 9 equals 1. But we have to be careful. The original question did not ask us to find S prime parentheses 1 and S prime parentheses 9. The original question was to find the rate of learning. So we should give our answer in terms of the rate of learning. What this sentence tells us is that after the student has been studying for 1 hour, their rate of learning new words is 3 new words per hour of studying. And this result tells us that after the students have been studying for 9 hours, their rate of learning new words is 1 new word per hour. Let's go on to the next part. Question B says to illustrate the result from A on the given graph. Let's go back up and look at those results from section A and think about how we'll illustrate them. In question A, we found this in words, but that corresponded to this symbol. Now let's go back up and look at our diagram. We found S prime parentheses 1 is equal to 3. That tells us that the slope of the line tangent to the graph at x equals 1 is m equals 3. So we'll illustrate that first result from part A by drawing a tangent line on the graph and indicating its slope. Well, it would be helpful to also know the y values on this graph. So when x equals 1, the y value is 6, and we know from part A that y prime parentheses 1 is the number 3. So that means we have to put a point on the graph at x equals 1 and y equals 6. So we'll illustrate this result by drawing a tangent line and indicating its slope. Now what about our other result from part A? Our other result from part A was this one about s prime parentheses 9. We'll illustrate that by putting a tangent line on the graph at x equals 9. It'll be helpful to find the y value on the graph first so we can label the point. So we need to have a point on the graph at 9, 18, and we need to draw the tangent line and label its slope. So notice the tangent line here is steeper than the tangent line here. So when the student's been studying for 1 hour, they're learning words at a rate of 3 words per hour. But when the student has been studying for 9 hours, they're only learning new words at a rate of 1 new word per hour. That makes sense. That's the end of that example, and that's the end of the video. Thank you.